Hello everyone. Today we are going to do a deep dive into diffusion models. This powerful family of models are widely used in most of the most popular multimodal LLMs today, including ChatGPT, Gemini, etc. And it is a key technical driver behind the latest wave of generative AI applications you are seeing across the tech industry. For example, midjourney, stable diffusion, etc. We will be covering topics including DDPM, DDIM, guided diffusion, latent diffusion, UNet architecture, and more. I will not only focus on the high levels, but also the training and sampling details, model architectures, and underlying math. Let's dive into it. Before we start, I want to say this talk is relatively math heavy. However, it won't affect your ability to understand high-level mechanism. It also won't stop you from experimenting. So if you don't understand, don't worry about it. I will cover topics including DDPM, DDIM, UNet, LDM, and other details. DDPM, denoising diffusion probabilistic model, is the original diffusion model. DDIM, denoising diffusion implicit models, and LDM, latent diffusion model or stable diffusion, its improvements built on top of the original DDPM. DDIM speed up the sampling process, and LDM improve the efficiency further by moving in a latent space. UNet is the model architecture that's used in all the diffusion models here. I will not cover some topics in details if those are covered in previous videos. For example, autoencoder deep dive, generative image overview, they should be in the same playlist on YouTube. It includes CNN basics, elbow basics, KL divergence basics, reparameterization basics. So just try to enjoy and have fun, just like you enjoyed this funny meme. Let's start with diffusion high level. Say we have 256 multiplied by 256 pixels to represent an image. So it's a square image. And each pixel have 3 color channels, RGB. We now have a space of 256 over 256 over 3 to represent images. So this space, let's say it's represented by this blue box. Within the space, each element needs to be specific values to form a meaningful image. Say if we want to form a sunflower drawing, all the possible combinations of sunflower drawings pixel forms a space or distribution. Let's say it's represented by this yellow cloud. If we can train a model with the capability to traverse back to the yellow cloud from any random point in the blue box, we will be able to generate images of sunflower drawing. And if we extend beyond one yellow cloud representing sunflower drawing to more space or distribution representing more kind of images, we will be able to generate any images. In order to train a model that's able to traverse from this random point back to the yellow cloud, diffusion is a very popular and effective idea. The idea is, first, we have the forward diffusion process, which is a point in the yellow cloud and slowly move out of the yellow cloud to the blue box, to a random point. And we use a machine learning model to learn the reverse process of this forward diffusion. Then we will be able to traverse back. Before we dive deeper into the details of diffusion model, one might ask, how was the idea generated? Did it come from nowhere? The answer is no. The idea is actually inspired by diffusion in physics. In physics, diffusion describes the net movement of anything, like atoms, molecules, energy, from a region of a higher concentration to a region of lower concentration. This movement is driven by a concentration gradient and the random motion of individual particles, often referred to as a Brownian motion. For example, a drop of ink spreading out in a glass of water. Initially, the ink is concentrated, and then the ink molecules randomly move and collide, gradually mixing with the water until the color is uniform, and we reach an equilibrium state. So the key inspirations from physics is the original DDPM paper studied the non-equilibrium thermodynamics. The process of gradually adding noise and then reversing it is very similar to a system moving away from and then back towards an ordered state, just like this. And diffusion is inherently a stochastic process. Diffusion models leverage the mathematics of stochastic processes to define how image is transformed into noise and how it's generated back from noise. So now you know this brilliant idea didn't come out of nowhere. It's actually inspired by something very common in the physics world. Now let's start with forward diffusion process in details. In forward diffusion process, image is transformed into pure noise, usually its standard normal distribution, like this one, in t steps. This is done via a Markov chain, where the image at timestamp t maps to its subsequent state at timestamp t plus 1. Each step depends only on the previous one. This is the definition of Markov chain, basically. Let's say we have two states here, xt and xt minus 1. The image in xt only depends on the image in xt minus 1, not to anything after xt. This is the formula that represents the transition from xt minus 1 to xt. Q represents the distribution. Given xt minus 1, distribution of xt is a normal distribution. And this is the expectation. This is the standard deviation. Gaussian noise, which is also standard normal distribution noise, is added at each step in the Markov chain. But it's not constant or random. Instead, the noise is derived from the structure of the original image, and the rate at which it's added steadily increases with each consecutive step. It's all determined by a scheduler. This beta t is the diffusion rate pre-calculated by the scheduler, and I here is an identity matrix. So in short, now we have a forward diffusion process. It's a Markov chain, and this is the state transition distribution, and the distribution is a normal distribution. The expectation and the standard deviation all depends on a beta t parameter, which is determined by the scheduler. That's it. If q given xt minus 1 xt is standard normal distribution, how do we add noise at each step since it's totally random? Can we just randomly pick every time? Say if we want to sample a noisy image in xt, can we traverse from x0 and randomly add noise at each step until xt? Yes, we can, but it means whenever we need a sample at xt, we need to iterate through the timestamp from 0 to xt minus 1 in the Markov chain. And if t is a very large number, this process is so slow. So an alternative is we can use the reparameterization trick. It's also covered in the autoencoder deep dive, along with the addition property of Gaussian distribution. Now let's take a look at the details of forward diffusion process. Let's say we have a new parameter alpha t equals to 1 minus beta t, and alpha t hat equals to the multiplication of alpha I from 1 to t. We can use reparameterization trick to get the formula of xt given xt minus 1. This epsilon t minus 1 is a random noise we sample from normal distribution. This is exactly the same with how we did in autoencoder deep dive. And then we can do the same expansion for xt minus 1, and this is the formula. And then we expand xt minus 2, and then we expand xt minus 3 until we get x0. So we have xt equals to this. So based on above, we have the distribution q given x0 of xt. It's also a normal distribution. This is the expectation, and this is the variance. Now, whenever we need a sample of xt, we can directly go from the original image x0, since all the scheduling parameters are pre-calculated. So we don't have to go through the Markov chain. By the way, the scheduler has several variances. So this beta t has many different versions of it. The original DDPM defines a linear schedule ranging beta t from 0.001 at timestamp 0 to 0.02 at timestamp t. There are other variances like cosine scheduler. This is the formula. And you can see different scheduler have a pretty significant impact on the efficiency of the diffusion. For example, cosine here probably work better than linear because it will be able to generate a clearer image with less steps from random noise. The next is reverse diffusion process. This is where the machine learning actually happens. The model is trained to reverse the forward process. So there's no machine learning in forward diffusion process. It's just Markov chain and mathematics. So in reverse diffusion process, the goal is we want to reverse the forward diffusion process. So we start from a random noise image, and we want to iteratively remove noise from this image. And after t steps, hopefully we can get the original image here. Directly transforming random noise into a new image is very difficult and complex, but transforming a noisy image into a slightly less noisy image is relatively easier. Thus, we start pure noise xt, it's a standard normal distribution, and gradually denoise it iteratively to produce a realistic image sample x0 here. The challenge here is we know the distribution of q given xt minus 1 xt from forward distribution process, but we don't know the distribution of xt minus 1 given xt. It's basically intractable to compute. This is because from Bayes' theorem, the distribution of xt minus 1 given xt equals to the distribution of xt given xt minus 1 multiplied by the distribution of xt minus 1 over the distribution of xt. We know this distribution from forward diffusion process. However, the distribution of both xt minus 1 and xt requires knowledge of the entire distribution of image qx0. This is the integral formula of the distribution of xt. And given it's doing integral on a pixel space, the space is too big, so it's just intractable to compute. How do we solve this problem? The solution is to approximate the true reverse transition with a learned model P, and theta represents the parameter. Typically, it's also a Gaussian standard normal distribution. The approximation distribution P theta of xt minus 1 given xt is this normal distribution. Expectation is a learned expectation, and the standard deviation is a learned standard deviation. This might sound familiar because we have gone through very similar process in the autoencoder deep dive. Now, this is a very important insight. Notice that although q xt minus 1 given xt is intractable, the posterior condition on x0, which is q xt minus 1 given xt and x0, is tractable. The intuition is the following. If you are given a very noisy image in xt, and you are asked to generate a less noisy image xt minus 1, it's basically impossible, right? There's infinite possibilities. However, if you're given x0, which is the original image, and a very noisy image in xt, then you're more comfortable of getting xt minus 1, which is a less noisy image. And I'm going to show you later that q xt minus 1 given xt and x0 is also a Gaussian distribution. This is the expectation, and this is the standard deviation. This is the detailed math deduction for the distribution q xt minus 1 given x0 and xt. This is from Bayes' theorem. If you're interested, you can pause here and take a look at the details. But in short, we find out q xt minus 1 given xt and x0 is normal distribution. And the expectation here is this formula. The standard deviation here is this formula. Given x0 equals to this from the forward diffusion process, we can pass x0 into this formula. In this case, we can get mu t hat equals to this highlighted formula. So it's a function of xt and epsilon t, which is the noise at time step t. Now we have several options on model's learning objective. We can either ask the model to predict the entire expectation, or we can ask the model to predict the noise at each time step epsilon t. And in the end, this is the option that the original authors pick. I'm going to explain later why. Anyway, the model's learning objective is picked to predict the noise at each timestamp. Then we have the model estimated expectation mu theta given xt and t to be this formula. Now, if you remember, our goal is to have an approximation distribution p theta xt minus 1 given xt. This is the distribution. It's a normal distribution. We have the expectation here. It's a parameter learned by model. What about the standard deviation? It's another parameter that we need to learn by the model, right? The DDPM paper found that fixing the variance to be beta t or beta t hat works well in practice. Using beta t hat is theoretically motivated as it corresponds to the true posterior variance, q xt minus 1 given xt and x0. Given the fixed variance that simplifies the model's learning objective, now we have the distribution of xt minus 1 given xt and t. Using the parameterized mean mu theta given xt and t and a fixed variance, a single step of the reverse process involves first, we use the model to predict the noise epsilon theta given xt and t using the trained neural network, and then we calculate the estimated mean mu theta given xt and t. This is the highlighted value, and then we sample xt minus 1. Since we know it's a normal distribution, we have the mean and we have the standard deviation, so we can use the reparameterization trick again. We sample a noise from standard normal distribution, and then we can sample xt minus 1. Sounds very simple, right? Now the next missing piece we need to figure out is the loss function. The training objective of diffusion-based generative models is equivalent to maximizing the likelihood or log likelihood of the sample generated at the end of the reverse process belonging to the original data distribution. It's a very long sentence, so I'm gonna read it again. The training objective of the model is equivalent to maximizing the likelihood of the sample generated belonging to the original data distribution. So to train our neural network, we need to define the loss function. In this case, is the objective function's negative. Minimize the loss function is equivalent to maximize the log likelihood. This is the integral formula of the likelihood, and this is our loss function. It's the negative of the log likelihood. This is intractable because we need to integrate over a very high dimensional image space over T as specified in this integral formula. So what can we do? We can do a very similar operation with the variational autoencoder. We can use the ELBO, evidence lower bound, or VLB, variational lower bound in this case. It's the same concept with two different terminology. Again, I'm gonna pause here for a second in case you're interested in the detailed deduction. This is similar from what we did on VAE. This is the loss function, and it's strict smaller or equals to this because now we add the KL divergence. And then in the end, we have the loss function VLB equals to this formula. So now our objective is transformed to minimize the VLB loss function here. We further expand the VLB loss function. In this deduction, we use Bayes' theorem again. And in the end, we can break this down into three parts: L0, Lt minus 1, given t from 2 to t, and then the last one, Lt. The first one is L0. This value is minor, and the original authors got better result without this. Let's ignore this from the loss function. Lt, this is the KL divergence between the distribution of the final step in forward process, Q xt given x0, and the first step in the reverse process, P theta x big T. Both of this distribution requires no model for learning. We can ignore it from the loss function since it's constant. So now we have the VLB loss function simplified to be the sum of Lt minus 1, t from 2 to big T. And after some math deduction by expanding the normal distribution, we can get a simplified loss function if we ignore this constant here. It's basically a mean squared error between epsilon t and epsilon theta given xt and t. Epsilon t is the noise generated in the forward diffusion process. Epsilon theta given xt and t, it's the noise predicted in the reverse diffusion process. So now the loss function is also really simple. That's a very long math deduction process. So let me summarize what we have to now. In the training phase, we need to go through the forward diffusion, and this is how we fast sample a noisy image at time step t given x0. And the simplified loss function is just a MSE error between the forward diffusion noise and the model predicted noise. And when we do sampling of noisy image at time step t minus 1, since it's a normal distribution with this as expectation, we can just sample z from a standard normal distribution and use reparameterization trick to sample xt minus 1. Now, before we go further details into the training and sampling steps, I want to use two questions to revisit what we have learned till now. First question is, why is the scheduler needed? Can't we just randomly add noise and denoise an image? There are several reasons we want a scheduler here. First reason is a scheduler is necessary for efficient training. Remember that the forward process Markov chain, Q xt given xt minus 1, depends on beta t being a fixed known constant for time step t. This is very important so we can directly sample a noisy image at any time step t based on Q xt given x0. So we don't have to go through the whole Markov chain just to sample a noisy image at xt. Second reason is it's necessary for reverse process with the simplified loss function. Remember the tractable conditional reverse step qxt minus 1 given xt and x0 depends on beta t being a fixed known constant for time step t. And we have gone through a very lengthy math deduction to get the simplified loss function, the MSE of the forward prediction noise and the model predicted noise in reverse diffusion process. So it also depends on the scheduler. The third reason is a carefully designed scheduler can affect model performance. For example, the first one is from the original linear scheduler. The second one is a cosine scheduler where the beta is shared in previous slides. And in this case, you can see the reverse process cosine scheduler will show a clearer image compared with linear scheduler. The second question is, why predict noise instead of predicting the whole image? The goal is to learn the reverse process p theta xt minus 1 given xt. So it's matching the true but intractable q xt minus 1 given xt. Why can't we predict the mean of the reverse process mu theta instead of the noise epsilon theta? The first reason is it simplifies the loss function. By designing the model to predict noise instead of the mean, the loss function can be simplified to a simple MSE form between the forward diffusion noise and the model predicted noise. This loss is a lot easier to implement and optimize and is mathematically equivalent to predicting the whole image, since the new image will be the previous image minus the predicted noise. The second reason is it has better scaling. The noise epsilon added at each step is sampled from a standard normal distribution. This means the target model is trying to predict always have a consistent scale and statistical properties, regardless of the time step t or the specific image x0. If we choose to predict the image itself, if t is large, xt is almost pure noise. And asking the model to directly regress from near pure noise to a highly structured, clean image with potentially large variation in pixel values can be very difficult. The scale and complexity of the image x0 can vary greatly, but the noise target epsilon is more uniform. Better scaling will make the training more stable. And the third reason, probably due to the first and second reason, it's just empirically working. Predicting noise epsilon just works. Now let's take a look at the detailed training process for diffusion. For each batch of the training process, first we want to sample a random time step t for each image sampled within the batch, and then we add noise from Gaussian distribution by using the closed form formula qxt given x0 instead of iteratively from time step 0 to t. And then we convert time step t into time embeddings, preparing to feed into UNet. I'm going to cover this part in more details. In short, time step t is convert into sinusoidal time embeddings, similar with what we did in Transformer. Next step is feed the time embedding along with the noisy image to UNet, so the UNet can predict the noise. The next one is compare the predicted noise to the actual noise to calculate loss function. And then we update the parameters of diffusion model via backpropagation and gradient descent. All those diffusion training process might sound very complex, but in pseudocode it's actually only a few lines. We repeat until converged. First we sample an original image from the original image dataset, and then we sample a time step t randomly from 1 to maximum time step, and then we sample a parameter epsilon from the standard normal distribution, and then we do gradient descent and backward propagation according to the simplified loss function. This is a more detailed PyTorch code. This function is the main function. First we use UNet, and then we use Atom to do gradient descent, and the loss function is just MSE loss. So for each original image in the data, first we sample the time step, and then we call this diffuse image to get xt and the forward diffusion process noise. And in this diffuse image function, it's basically calculating this. We have square root alpha hat, square root 1 minus alpha hat, and then a epsilon sampled randomly from standard normal distribution, and then we return xt and the forward diffusion noise. And then we use xt and the time step t to calculate the predicted noise using UNet. And then finally, we calculate loss function with the MSE. With the loss function, we will be able to do gradient descent and do backward propagation. This is a more visualized view of what happened in the training process. Let's say we have a lot of images in the original training dataset. During training, we randomly sample a time step for each of the image and transform those time step into time embedding. And then we use the forward diffusion closed formula to calculate the noisy image. along with the time step. And then UNet will be able to predict the noise, and we already know the actual noise. So we will be able to calculate loss function by comparing these two, and then update the model parameters. This is the sampling process. For sampling new image with the model, first we need to sample a random noise from Gaussian distribution to have a random starting point. And then we need to define how many time steps to generate the new image, say 1000, which is a typical value. And for each time step, the diffusion model predicts the whole noise presented in the current image. And then we only remove a fraction of the whole noise as defined by the scheduler. For example, to get xt minus 1 from xt, this is the formula. And epsilon theta given xt and t is the noise. So we only remove a fraction of it, and the fraction is basically this. And both alpha t and alpha t hat is a function of beta t. So everything is defined by the scheduler. And then we repeat this process for 1000 times to generate the new image. The pseudocode is also very simple. First, we sample xt from standard normal distribution, and for t steps, for each time step, we randomly sample z from standard normal distribution for a reparameterization trick, and then we calculate xt minus 1 given the predicted noise. And we repeat this for t times. It will return us the original image x0. This is the sample code from PyTorch. We are using an image space of 256 to 256 pixel, a square image, and then we have 3 color channels. For each step, in this case noise step should be 1000, we have a predicted noise, and then we calculate xt minus 1 given the predicted noise and alpha. This is a visualized view of diffusion sampling process. Let's say we first sample random Gaussian noise for t equals to 1000. So this is x1000. It's just pure noise. And then we iteratively remove noise for t times. For the first time, we pass in t equals to 1000 time step, transform it to time embedding, and then pass in x1000 to the UNet. And then it will predict the predicted noise. And then we subtract this value from x1000 and get x999. And then we repeat this for 1000 times. In the end, we should get one x0 image. Basically, x1 minus the predicted noise equals to x0. Now we're done with DDPM. Let's take a look at DDIM. The original version of diffusion is called DDPM, Denoising Diffusion Probabilistic Models. The sampling is pretty slow since each time step is a stochastic Markovian process. The current state only depends on the previous state, so we can't skip any state. And we need to iteratively go through many time steps just to generate a new image. Previously, we are using 1000 as example, and it sounds way too long. DDIM aims to solve this problem. The training process and objective is identical with DDPM. The only difference lies within the sampling process. DDIM accelerates the sampling process since it allows much smaller sampling steps. Let's compare DDPM and DDIM. For DDPM, it's using 1000 steps for sampling. DDPM won't be able to skip any of the steps, so it needs to go one step by one step until it reaches x0. However, for DDIM, we will be able to define a pre-selected steps. Let's say we only want to sample 50 times, and then we can use a pretty common partition strategy, which is uniform. So then the 50 steps will be mapped to x1000, x980 until x0. There's also non-uniform partition strategy. For example, spend more steps in the later stage of sampling or use a model to learn the optimal partition. You can do that, but the most common one, the uniform partition strategy, just works. So you only calculate the parameters for those pre-selected steps. So why can DDIM do this? Let's take a look together. The DDIM paper have a very sharp observation. For DDPM, the distribution of qxt given x0 is very important. Almost all the following conclusions depend on this formula. This is still a tractable Gaussian, regardless of whether the forward process is Markovian or not, as long as the forward process can be expressed as adding noise scaled by 1 minus alpha t hat square root. This distribution is what the DDPM training objective, specifically the simplified noise prediction loss, primarily relies on. If you remember, when we go through the diffusion process, we mentioned we want to consider this a Markovian chain, but when we do the mathematic deduction, all it matters is this, as long as the forward process can be expressed as adding noise by this scale. So DDIM considers a more general, non-Markovian forward process. The goal is still to define a reverse process that can generate x0 from xt. However, unlike DDPM, which derives this based on the fixed forward Markov chain, DDIM tries to directly propose a implicit function, xt minus 1 equals to the function of xt and t. So how do they come up with an implicit function here? From qxt given x0 is a normal distribution, we can get an expression of x0 given xt and epsilon t. Now, DDPM's trained model predicts the noise epsilon theta given xt and t, so we can actually use the trained model to estimate x0. The x0 estimation is a function of xt and epsilon theta xt given t. This is a typo, it should be DDIM. DDIM proposed a new general form based on the above estimation and a new variance parameter sigma t. Xt minus 1 equals to this expression. It's a function of x0 estimation, sigma t, and a random noise sampled from standard normal distribution. It's very similar to DDPM with slight difference. Now let's substitute the expression for x0 estimation with this expression. So we will be able to get xt minus 1 equals to this huge expression. And you can see the intuition here is it's a combination of predicted x0 and a direction pointing to xt and a random noise here. So the advantage here is first, it allows flexible sampling. The parameters sigma t introduce flexibility in the reverse process. When sigma t equals to 0, the reverse process becomes deterministic. This means that for a given initial noise xt, the generated sample x0 will always be the same. Second, more importantly, it allows accelerated sampling. Since the dependency on Markov chain is removed, DDIM allows for sampling with much less steps, s is much smaller than t, by selecting a subsequence of time steps, tau1 from tau s. The reverse process then only needs to be computed for these selected time steps. The relationship between DDIM and DDPM is a subset of DDIM. By setting sigma t into a specific value, DDIM reverse process will become equivalent to the DDPM reverse process. If you think about it, this makes sense because Markovian process is actually a subset of non-Markovian process. We have gone through a lot about DDPM and DDIM, so this is a quick comparison between those two. DDPM is Markovian, DDIM is non-Markovian. For DDPM, it requires qxt given xt minus 1 to give the distribution of qxt given x0. And DDIM actually relies on qxt minus 1 given xt and x0 to come up with the estimation for epsilon theta. The reverse process type for DDPM, it's a stochastic approximation to qxt minus 1 given xt, and DDIM is trying to get an implicit function of xt minus 1 given xt and t. For sampling, since Gaussian noise is added in DDPM, it's stochastic. However, for DDIM, if we set sigma t to 0, it's deterministic, so no stochastic. And for sampling speed, DDPM is slow. DDIM usually is a lot faster. And for training objective, both DDPM and DDIM shares the same objective loss function, which is a MSE loss between the forward diffusion noise and the model predicted noise. Now let's take a look at the model architecture for DDPM and DDIM. In the core of diffusion model, it's UNet. Diffusion uses UNet-like architecture to predict noise of the image, where the output size equals the input size. Original UNet get the name from the U shape in the model diagram. UNet shares architecture similarity with autoencoders, including downsampling, upsampling, bottlenecks, etc. So if you're interested in the original UNet, this is the architecture. It has convolution, activation function, max pool, etc. Diffusion model's implementation contains some modifications to the original UNet, including residual blocks or skipped connection, if you're more familiar with that name, and multi-head attention and time step embedding, etc. Residual blocks preserve spatial details when downscaling features. Time step embeddings make diffusion model aware of the different time step and level of noises need to be added. Multi-head attention better capture the relationship of original image feature to predict noise better. This is a simplified version of diffusion model's UNet. The input is a noisy image and a time step. In this case, it's sinusoidal embeddings. It's very similar to what Transformer does. And for the first half of the UNet model, we have downsample blocks, we have self-attention blocks, and we also have skip connection to the upsample blocks. So we can pass in some spatial details, which could be neglected when we do downsampling. And this is the bottleneck. It also contains some architecture that I will be going through in later slides. And upsample blocks is very similar, but the reverse. It has upsample blocks and self-attention blocks, and it received a skip connection from downsample blocks. Now I'm planning to give a more detailed view of each module within the diffusion UNet. This is a very good website that implements a diffusion UNet. So if you are interested, you can go to this website and take a look at the details. This is the UNet main function. It tries to get the time step embedding. It goes through the first half of UNet. It goes through the bottleneck, and then it goes through the second half of UNet. And before we return, it goes through a group normalization and then another activation function. The activation function, swish, is basically x multiplied by sigmoid, and this is the shape of the swish function. This is a pretty popular choice. And normalization function is group normalization. We have been going through batch normalization, layer normalization, RMS in the Transformer deep dive, and here it's a new normalization function. It's called group normalization. It divides the channels of a feature map into groups and then normalize each group independently, reducing the dependence on batch size and improve performance across different batch sizes. Diffusion models, particularly those using UNets, can process images of varying sizes or solutions, so independent of batch size is very important. If you remember, the motivation of layer norm is also to handle different batch sizes better. So can we use layer norm? Actually, yes, we can use layer norm. It's also independent of batch size. However, group norm is usually preferred since it's cheaper than layer norm. You can consider group norm needs a global parameter and layer norms needs multiple local parameters. Otherwise, they're pretty much similar. The time embedding here is using sinusoidal position embeddings similar with Transformer. Basically, this is the mathematical expression. And embeddings goes through MLP for complex nonlinear pattern learning. It calculates the sinusoidal math expression, and this is the MLP. The first layer is a linear layer, and then it goes through nonlinear activation function, and then the output layer is also a linear layer. And then we can finally return the time embedding. Now let's take a look at the first half of UNet. First half of UNet, it goes through down blocks, which contains residual, skip connection, and multi-head attention, and then it goes through downsample blocks. This is the definition of down block. It goes through residual block, and then it goes through attention blocks. This is the definition of downsample. It's pretty much very straightforward. It's doing convolution to cut the feature map by half. This is also covered in my Gen AI overview video. Next is the bottleneck part. The bottleneck combines a residual block, a attention block, and then followed by another residual block. This block is applied at the lowest resolution of the UNet. That's why it's called bottleneck. And the definition is also pretty straightforward. You define the residual block, attention block, and another residual block. And then the forward function is just to pass through all those three blocks. Then let's take a look at the second half of UNet. It goes through up blocks, which contains residual or skip connection, and multi-head attention. Then it goes through upsample blocks. It's very similar to down block, just the reverse. This is the definition of up block. It also combines residual block and attention block. This is the definition of upsample block. It's using transposed convolution to scale up the feature map by 2x. This is also covered in Gen AI model overview. Alright, this is everything I want to cover for DDPM and DDIM. Hope it's helpful. Now let's move on to other topics. So up till now, we have gone through DDPM and DDIM, and we are not able to control what we generate. For example, there's no way for us to give the model a sentence, let's say number 4, and then ask the model to generate an image here. So what if we want to gain some control in what to generate? This is where the guided diffusion model come in. The idea is very similar to guided variation autoencoders When we do training, other than the actual noise and time step embedding, let's also feed in a embedding that represent a text or query and feed those into the UNet. So after training, the UNet, which contains self-attention blocks, will be able to recognize the text query as its context. So when we do sampling, other than a random noise, we also pass in another embedding represent the query that you want a model to generate. Let's say in this case, it's number 4, but in another form. It's not in training data, but it shares a very similar embedding. So the trained UNet will be able to predict the noise and then iteratively remove the noise and generate an image that represents number 4. Pretty straightforward, right? There are something even more powerful. If you have used Stable Diffusion or Midjourney, they're using diffusion models, and you can pretty much control anything that you generate. Is it using guided diffusion models? No, they're not. They're using something called LDM, latent diffusion model. So let's start from the beginning. The motivation of latent diffusion model is training and sampling of diffusion model can be very expensive, computation and memory-wise, since it requires multiple denoising passes. Can we introduce a lower dimension latent space and perform diffusion there? Stable diffusion is motivated by this and performs the diffusion process and reverse diffusion process in the latent space. This is the TLDR of what LDM is doing. It trains an encoder for encoding a full-size image to a lower dimension representation. That is the latent space. And then the forward diffusion process and the reverse diffusion process is within the latent space. We also train a decoder that can decode the image from its latent representation back to the original pixel space. This is what it does. Original image goes through encoder, becomes a latent data with smaller size. And after we do forward diffusion process and reverse diffusion process, we transform this latent data back to the original pixel space via a decoder. Now, what makes LDM more powerful is the conditioning with cross-attention. Let's do a recap of what cross-attention is in the transformer architecture. If you're interested, you can take a look at my deep dive video. But this is basically the cross-attention block. And as you can see, the keys and values are from encoder and the queries are from decoder. The intuition is it wants to find out for a given decoder query what encoder information is the most important to pay attention to. And Stable Diffusion is using cross-attention as its core. This is the graph of latent diffusion model. In the pixel space, we use encoder to encode it to the latent space, and then the latent space output use the decoder, so it's back to the pixel space. And in the latent space, we do diffusion process from Z to ZT, and then we do reverse diffusion process from ZT to Z, and it's using UNet to predict the noise in the latent space. And within the UNet, it actually contains the attention block like we discussed before, the QKV here, and the conditioning is taking advantage of this cross-attention block. So Stable Diffusion model can generate images from text prompts. The inner diffusion model is turned into a conditional image generator by augmenting its denoising UNet with the cross-attention mechanism. Text inputs are first converted into embeddings using a language model, tau theta, right here. You can use BERT or CLIP, and then they're mapped into the UNet via the multi-head attention layer. Key and value are from text prompts. Query is from the latent representation of image. Other than text, you can actually put in other type of data, semantic maps, images. For those, the condition is done using concatenation. Now let's take a look at the training for LDM. LDM training is two-phased. Phase 1 is it trains a autoencoder to reproduce lower dimension representations. And in this case, it's not using the regular VAE, it's using VQ VAE, vector quantization VAE. This diagram is the diagram for VQ VAE. It is very similar to a regular VAE. The biggest difference is the codebook here. VAE uses a continuous latent space, as we covered. However, VQ-VAE uses a discrete latent space, represented by a learned codebook. The codebook is a learned vocabulary or dictionary of embedding vectors. It is a finite set of k vectors. Each vector, often referred to as a code vector or embedding, has a specific d dimension. These k vectors represent the possible discrete states that VQ-VAE's encoder can map its continuous output to. You will understand the difference more when we go through the VQ-VAE workflow. First step is encoding. The encoder processes the input data, for example, an image, and produces a continuous latent representation. This is identical with the regular VAE. The difference is next step, quantization. So instead of directly passing this continuous representation to the decoder, the VQ layer steps in. For each vector in the continuous latent representation, it finds the closest matching vector in the codebook, like a dictionary, based on the distance metric. Usually you can use edit distance. Now you do discrete representation instead of the original continuous representation. The index of the closest codebook vector is then used for that part of the input. Effectively, the continuous vector is quantized to the nearest available codebook entry. And then decoder receives the selected codebook vector and use it to reconstruct the original input data. So what's the benefit of using VQ-VAE instead of the regular VAE? First one is VQ-VAE usually have more meaningful latent codes. VQ-VAE quantize the encoder's output to the nearest vector in a learned codebook. This forced the model to pick a specific discrete representation from a finite set. Each codebook vector can potentially represent a recurring pattern or concept in the data. This can lead to a more interpretable and structured latent space. This is a big advantage, especially if you're generating categorized data. For example, you want to generate image for cats, for dogs, and it will be very convenient if your codebook contains those embedding. VAE maps to a continuous distribution. It can sometimes lead to less distinct or fuzzier latent representation. The second one is avoidance of posterior collapse. From the name, you can know this is a bad thing. This happens when your decoder is more powerful than your encoder. This is where the latent variables become not informative and the decoder learns to ignore them, relying mostly on its own parameters. The KL divergence can actually make this even worse. In the VQ-VAE, the model is forced to use the information encoded in the selected codebook to reconstruct the input. So this ensures the latent space remain informative. And the last one, VQ-VAE is more computational efficient because it has higher compression ratio. The sequence of discrete latent codes is much smaller than the original data or the continuous latent space. Also, the discrete tokens produced by a VQ-VAE is well suited for sequential models like diffusion decoders. Phase 2 is very similar to a regular diffusion. It uses trained encoder and decoder to perform diffusion. It's very similar to DDPM with only a few differences, like input is in the latent space and it has the conditioning cross-attention. Conditioning through cross-attention layer operating on conditions input embeddings from encoder tau theta feeding into keys and values. So the query here is the latent representation of image. Key and value pass in the encoder tau theta, which is the word embedding for text. And the loss function is also with embedding. It's still a MSE between two losses, but the model is actually taking conditioning as its parameter. This is a visual of the LDM phase 2 training. The original image is passed through a trained encoder, and now we have a latent space representation, which is smaller than the original size. And then it goes through forward diffusion, same with what DDPM does. It adds noise to it. And then let's say for this training process, we sample the time step to be t. So we get zt here, and then we pass in time step t to get the sinusoidal time embedding. We also pass in conditioning. Say you have text or semantic maps or images. A very common way to do is if you scrape an image from online, most likely there will be some text or additional information surrounding that image. You can scrape those texts and pass in as conditioning. It will go through this encoder tall, and we pass all those information to UNet. ZT, a noisy latent representation of image, time step embedding, and conditioning embeddings, and it will predict the noise. Then we compare this predicted noise with the actual noise added in the forward diffusion process using the simplified MSE loss function. This is a visualization of how sampling looks like in LDM. Again, it's very similar to how DDPM or DDIM does. First, it starts at the maximum time step t. We transform this into a time embedding, and then we randomly sample a latent representation from standard normal distribution, and now we get Z big T. And then we pass in the condition and embedding. In this case, for example, you want to generate an image of a cute cat. So just pass in the text cute cat as conditioning, and it will go through the encoder tall and transform your text conditioning to text embedding. We pass all those input into the UNet and do reverse diffusion, repeat for T times. And then it will give us the latent representation of the generated image Z0. We pass this into the train decoder and it will give us the generated image. Since the size of the latent space is a lot smaller than the original image size, the denoising process is very fast. Alright, this is the last slide I have, and now we have gone through Stable Diffusion 2. Hope this video is helpful, and if you like my video, please subscribe, comment, or like. See you next time.